Hey, welcome back to the Moonshot channel, where we use the engineering design process to solve cool problems using modern technology. In the last episode, we generated a list of concepts for ways that we can more accurately predict the track of hurricanes. In this episode, we'll dig into those ideas and try to figure out which one or which ones we want to combine together to build on for our preliminary design. Now, I was about to shoot this episode last week, but I've been neck deep in data, experimenting around with several APIs and datasets and testing them out with a couple different algorithms. Actually, as I've been diving into it more, I'm realizing that it probably makes sense for me to cut this step into 2 episodes instead of 1. I think I'll still be able to get through the whole series in 10 episodes still though, because a lot of the code that I've been putting together for this step will form the foundation for our final design. Anyway, I'm going to get into all this in more detail shortly. For now, let's get back to our mind map from last time. Now, how do we go from this, which is a loose collection of ideas, or really fragments of ideas, none of which is really a solution to our problem in itself, to a system that can predict the track of hurricanes? Well, first, I think we need to categorize some of these ideas a bit better. At a super high level, there are 3 real components that any solution we come up with will need. First, there's the data source that we use to train our system. Second, there's the data format that we store it on our computer, which dictates how quickly our system can really train. And third, there's the specific set or specific algorithm that we want to use to draw the connections between the variables. Now, what we need to really do is dive into each of these 3 categories and assess the ideas within each and come up with the best combination of ideas, the best data sets, the best way of storing that data, and then the best algorithms that all work together in order to form our core foundation for a preliminary design. So let's dive into that. So first, diving into the data sets here. We have a lot of different data sets that we can choose from here. The first that I want to talk about, because this is something that we're going to have to use regardless of any of the other data sets we go with, is the HURRDAT-2 track data. Now, this is provided by National Hurricane Center within NOAA, and this is basically the sets of latitude and longitude coordinates that go along with the center of each storm every 6 hours. And this goes way back, farther than any of the available data sets. So we have track data that spans most of the 1900s and then goes right up until the end of 2017. Now, we don't have anything for 2018. I'm not exactly sure why. I mean, we're well into 2019 at this point. You would have thought that they would have at least published the 2018 data by now. I do know that there are ways of getting the live center of a storm, so we will be able to, once we train this thing, we'll be able to use it live. So that shouldn't be a limitation. But this HURRDAT data only goes through the end of 2017. And this is important to keep in mind too, because when we benchmark our results against those of other systems, those benchmarks look at the 2013 through 2017 results. And that's the reason why we just don't have HURRDAT data for 2018 yet. Anyway, so we'll definitely be using HURRDAT-2 regardless of anything else. Station data is another story. Now, this is numerical, like CSV files that correspond with the, say, pressure, temperature, wind speed readings from each of the land-based weather stations around the world that NOAA has access to. And there are also buoys out at sea. I should really categorize those here as well. Similar data we get from there, but those also include information about waves. So this weather station data is very interesting, but I will say that there are problems with it. Whenever there's a null value, which happens quite often, they fill the values in with 9s. So, and I forget exactly the number of 9s, if it's 5 9s or 7 9s or whatever, but it's a numerical value. And this is going to be, I think, a problem. Could be a problem during training. It's not going to throw an error. In fact, it would allow that value in. I can have outlier scrubbing in place to prevent that from happening, but it's just I prefer to see null values in data sets when there's stuff that's missing, or a string or something that would throw a flag and is easy to catch. But regardless of any of that, this is potentially useful data, but I think there are other data formats that are more conducive to training a neural network, and I'll get into those in a minute. Next up is the ERA Interim and Reanalysis data set. Now this reanalysis data set, and there's also one from NOAA that I'll talk about shortly. What reanalysis means is it's essentially taking modern physics-based models and using that in combination with historic sensor data to sort of fill in the gaps between physical weather stations. So, you know, we have a lot of weather stations over land. We don't have so many over the ocean. We have weather buoys, but there aren't that many. So these reanalysis data sets allow us to look back in time and see every either hour, every 6 hours, what the temperature, pressure, wind speed, etc. all were at various grid points around the world. And this is both in terms of latitude and longitudes, but also at different pressure levels. So this is a very, very useful set. It's gridded, and I think that we want to use it. And this is what everyone else has been using, and I think there's a good reason for that. It's the ERA Interim Reanalysis data. Now, one thing to point out, though, is that now there is ERA 5, which is replacing the ERA Interim Reanalysis data set as of later this year. And with the ERA Reanalysis data set, there's also a time lag, so you can't get live ERA Interim Reanalysis data, which would be a problem if we wanted to actually use this to forecast current storms. ERA 5 does not have that limitation. It's near real time. So this is there are a lot of reasons to go with ERA 5. ERA 5 is also higher resolution. The weather models have been updated. ERA Interim Reanalysis data is 10 years old at this point, whereas ERA 5 is state of the art. And yeah, it's also accessible by an API. So, I mean, it's just going through these bullets. I mean, it is the gold standard. The history goes all the way back to the 50s, 1950 to present. I talk about how it's gridded, and there's an API that we can use. That API also coincidentally has been written so that we can get this data very quickly. So they understand that the amount of data that they have on hand is, I mean, it's too much to do bulk downloads. They have a whole section on their website about that. So, you know, ERA 5, the API for accessing it is designed to work quickly, so we can basically access the data as we need it. And there are so many variables to choose from, including wave direction and all that. As I was saying, the size of the data, though, is massive, 11 terabytes per month. We can't download that. So if we want to use the ERA 5 data set, we're going to have to find a way to basically access it live via their API. And I'll get into more of that later. Okay, getting into the NOAA reanalysis data now. This one's free. I mean, the ERA interim data is also free. I should point that out. I actually originally thought it cost $3,500 because I ended up going to some landing page on that site, and they talked about API access, and if you were using it for individual personal use, it was $3,500. But it turns out the ERA 5 and ERA interim data sets are free through that source. So that was a mistake on my part. I wish I had read that a little more carefully in my first visit and dove in a bit earlier on in the process, because it is an awesome data set. But the NOAA Reanalysis 1 and 2 data sets I had kind of moved forward on. I downloaded them from the archive site. You can access these through the NOAA Data Access website, but I found that the file format from the archive site was something that I already had set up to open. So, you know, this is something that you can find pretty easily, and they have various resolutions depending on if you use ERA Reanalysis 1 versus 2 that go back and cover different historic coverage periods as well. But they both go back several decades, and they're both gridded, but if you choose to download them through the FTP sites, it's pretty slow. All the NOAA FTP sites are pretty slow. They seem to limit your download speed per IP address or whatever to 1 megabit per second. So it's going to take a while to open. And depending on the file format that you go with, it may be a little tricky to open it. I'll get a little bit more into that with the gdas file format, which is a little different. A lot of these there are a lot of choices with the NOAA Reanalysis sets, but I found that all of these file formats were a little tricky. Accessing data via an API is a little more straightforward on the other hand. So that's just something to keep in mind. Anyway, so I'm going to hop over to the gdas data now, and I'll come back to the satellite image data in a second, just because gdas has a lot of the similar issues. So gdas is sort of the current version of Reanalysis 2. This is the global, I think it's global data assimilation system or something. But what it means, what it does is it takes data from all these different sensor systems and satellites that we have, including aircraft and ships out at sea. And all that data is brought into a live real-time physics model that does a lot of the same stuff that ERA5 does. It uses modern physics models to fill in the gaps between data points so that we have a gridded output that we can use. The gdas data files, though, as you can imagine, are very, very large, and they're also slow from the same FTP site that I was talking about before, the archive site. And then the format that they come in is, it's odd. It's not grib. If I remember offhand, I think maybe some of the reanalysis data, that might be grib. But I have to go back and check. I know Wavewatch III for sure is grib, and you know, if we go in bulk download some of the ERA interim data, that is grib as well. And grib is also problematic in that you can't install pygrib, which is the reader that you need to open a grib on a Windows machine. I mean, you can, but you have to compile from source, which is a pain. So you know, it requires that you run this in Linux, which I think most people that are doing machine learning do have a Linux setup in some way. It's generally a thing that you ultimately need to be able to load certain libraries. But the gdas file format is different, and it requires this unofficial Python script that I had to download from GitHub. It seems to work, but I did have some issues. When I opened the files to begin with, the orientation was off. You know, I had to do a couple operations. I rotated and then flipped to one of the axes. I mean, you could probably just, I think a transpose would do the same thing. But either way, you know, it wasn't completely obvious that the data was formatted like that. And so, you know, I had to use a visualization tool to view that data and make sure that the latitudes and longitudes all matched up with, you know, the values that they corresponded with. So I can show you this kind of cool tool that I was able to repurpose. This is a 3D view, globe of the world, and I wrote up some code that you know, took this. I didn't write all the core code. Full disclosure, I'll put a link to the original source code for it. But I modified it so that it can interface with my local copies of the gdas data, which I have saved in a MySQL database, which I'll talk about in a minute. And you know, this allowed me to basically troubleshoot and make sure that the latitudes and longitudes were all being saved correctly. It also is a way that I can go through and ensure that the data quality is consistent. So anyway, that's gdas. Going back to satellite image data, there are a lot of sources for this. I mean, NOAA maintains a site. There's also data you can get from NASA. It is a little clunky. I found numerous FTP sites, and it's not entirely obvious what you're getting. You have to do a lot of research to figure out what satellites provide what data, what sensors they have, etc. But there is this one site that I found that provides mosaic data. It's a composite, a world view composite that takes satellite imagery from numerous different satellites around the world and stitches them together to give you a full world view. And one thing to note with this, though, is that you know, the day-night cycles really do black out the dark side if you're looking in the visible spectrum. And I just imagine this being problematic for a lot of reasons when we're trying to use convolutional neural networks or whatever to view this and do something with it, do something meaningful, extract, you know, future latitude and longitude coordinates or whatever. But there is a water vapor sensor grid of some sort. I'm not exactly sure how it works, if it's just a different spectrum of light that this is observing, maybe microwave or I don't know what, but something that allows these satellites to view, water vapor content in the atmosphere, and that view doesn't seem to be affected by the day-night cycle. So I downloaded those. That was my priority, and I actually used them. I'll get more into that later, but I used them with a generative adversarial network to see if I could take an existing snapshot view of the world and then forecast what it may look like in the future. So I'll get more into that a little later, but that was pretty cool, and it opens up some ideas for what we might be able to do down the road. Oh, one other thing I want to note, satellite image data was a little dirty. There were basically text labels on certain sections of the image, the composite image, saying what satellite it came from, and that obviously isn't ideal for our purposes. And in addition, sometimes there were missing areas of the world that would show up as sort of like washed out in one color or another, and that it's all just not really ideal for what we would want. But it's pretty interesting, useful stuff. Okay, next, Wavewatch III. Now this is actually what I found way before I found the archive for the reanalysis data from NOAA, and I was able to bulk download this really quickly and extract it and save it to a MySQL database, which allowed me to kind of experiment around with gridded data using some of these algorithms without having to go and wire something up to, say, the ERA5 API. This was just really quick and easy to use. So I downloaded all that. It's got decent historic coverage. It's gridded, but the only problem is that it only provides data over the oceans, and a lot of this data in theory should be the same as what we see from GDAS. We have pressure, temperature, all that, and that all gets fed into the Wavewatch model, and that Wavewatch model then in turn calculates things like wave height and wave direction and all that sort of stuff. And we get all that through the ERA5 as well, at least from reading the documentation for it. It's just they don't have separate models, whereas NOAA has separate models. NOAA has this gdas system, and then they've got this Wavewatch model that kind of extends the gdas system to also give you information about the waves. So, if we went with the NOAA route, we would really need to use both GDAS or Reanalysis 1 and Reanalysis 2 along with Wavewatch 3. Whereas with the European set, I believe we'll be able to get all that same data just from GDAS, or not GDAS, I'm sorry, from the ERA5 data set. But one thing to note though are these files are in grib format, which, as I was talking about before, requires that you open them in Linux. And I wrote a script to do that, to extract all the data that I wanted from those grib files and then save it to a MySQL database that I was able to access from my Windows machine. You could also access this on a Mac or whatever as well. But this saving to a MySQL database I found to be necessary because the grib file format is both clunky, it saves way more data than we would need, and this also goes for the GDAS data set. Those are massive files, and we have way more variables saved in each of those than we would actually want to use. So if we want to run a training algorithm and then open each of these files one at a time, I mean, we're spending a lot of our time opening and reading data that we don't need. So extracting just what we want and saving it to a MySQL database really helps speed things up. Now next, the alternative data sources. I talked about these a little bit last time. There's radar data and seismic data. The radar data can be used to show a flight path of birds, and my sort of theory last time was that perhaps the migratory patterns of birds might tell us something about the atmospheric winds that we wouldn't necessarily know about because we don't really have a whole lot of sensors up in the sky other than airplanes. And if we had that data available, maybe it could provide us with a better model of the atmosphere, which could tell us more about what the storm may do. But that said, it only extends slightly over the ocean, and for that reason, I'm not really going to waste too much time digging into it. I think I'm going to skip integrating that for now. If we find when we get to the end of this process that our model still isn't performing as well as we'd like, maybe we'll revisit that. But for now, I'm just going to say, too much effort with too little potential reward to try to integrate that weather data. Same with the seismic data. The seismic data, the format just really isn't easy to work with. I couldn't find an archive that provided easy to access seismograms or whatever they're called. And so I don't want to, really spend too much time looking at that either at this point. But I do think there's potential for doing that in the future. And I certainly hope that NOAA and the EU group are looking at, doing something with it, because it would be really cool. All right, so data format. Now this is what is going to essentially dictate how quickly our algorithms can train. How quickly does a sample get loaded from a physical hard drive or whatever. And that is oftentimes the bottleneck in any machine learning training process. So we have a lot of different ways we can do that. And not all of these really are local storage options. I'll get into this in a second. I'll start with the MySQL database because I already have this set up and I use it all the time for machine learning tasks. And essentially what I'm able to do very easily in Python, thanks to Pandas, is I'm able to essentially take what data I want, from say a big file like a gdas file or a grib file, extract just the variables I want and then save them to my SQL database. And that allows me to, pull just later on just the samples that I want with just the variables very quickly. And I can do that on multiple machines across multiple threads that are all accessing this database all at the same time. And so that lets me, run machine learning over a cluster. I mean, that in combination with other tools like RabbitMQ, which maybe we'll talk about, probably not this episode, maybe this episode, but certainly in the next one. Setting up a cluster is a little bit of a pain, but once you've done it once, it's easy to do the next time. And it can really boost your training speeds. But MySQL database, I find, is a key piece of that. Also, one thing to note is that there are certainly limitations with this. It's best to have a MySQL database loaded on a SSD drive, for obvious reasons. The read speed and write speeds are a lot faster. When it starts getting really big, though, as I'm finding it's happening with me right now, you may have to move it to a hard disk drive. I actually had to buy a 4 terabyte drive, which is where I've saved my SQL database to now, because some of this historic data, the Reanalysis 1, Reanalysis 2, and gdas data are just absolutely massive data sets. So anyway, that's this option. I'm going to use it, at least for this proof of concept step. Again, just because I already have it, but if you haven't set it up, just hold on, there are some other options. Also, eRay5, this is, as I was talking about before, they have this on-demand API access system that they've built, and in theory, they're pitching this as, instead of having to bring the data to us, the user, they want to bring the user to the data. That's how they frame it. So theoretically, this has been designed to be very fast and responsive. I haven't yet really fully tested it yet. I've been working a lot with the data sets that I had enough hard drive space to save, because I have my reservations. I feel like I'm probably going to hit some speed limits here. Either they're going to limit me based on my API key, or maybe my own internet connection, which is a 100 megabits per second down, and I think like 50 up. That may be a limiting factor here, bottleneck as well. Because they say that it's something like 11 terabytes per month is how much data that this thing holds. And we're not obviously going to be using most of that, but it's very high resolution, much higher resolution than even gdas, which is high resolution than the Reanalysis 1 or Reanalysis 2 sets. And that's a good thing, but it also means that the amount of data is absolutely monstrous. So I'm gonna have to do some experimenting. That's gonna happen this week. So in part 2 of this, I'll get into, the results of that. Okay, so the other option, you can obviously just leave these files alone, the grib and the gdas files just saved on your hard drive and try to access them. But as I was getting at before, these files contain a lot of data we don't need, and you're gonna spend a lot of time opening them, because you're reading data that you don't need. So I wouldn't recommend doing this. Don't do that. Instead, take what you need. If you don't want to set up a MySQL database, take what you need out and save it as a local file, either a pickle, a CSV, or a local image file. Now I'm talking about image files right off the bat here. Okay, image files are interesting in that we can save numerous channels with an image. And what I mean by that is the way that a JPEG image works is we have 3 color channels typically, red, green, and blue. And so each of these is essentially a black and white image, and they all get superimposed over each other and associated with a specific color. So we can leverage that sort of inherent way in which a JPEG works to save at least 3 variables there. And I believe in the paper that I read on the fused network approach, they did that with the WIN components. So they had the U component and the V component were each a color channel in an image that was saved. But then the pressure they brought out into a whole separate tree. They mentioned something about how the learning rate had to be different for the pressure variable. That's interesting. I guess I'm going to have to dive in a little bit deeper to maybe see what they ran into on that front. But I would think that we'd be able to save the wind speed and the pressure. Each is a different color channel within one image. So U component, V component, and pressure in a 3-channel JPEG image. The other thing with image files is that each pixel and each color channel within the pixel is limited to being an integer representation between typically 0 and 255, depending on the sort of bit rate or whatever of the image. So in our case, we have right now with our MySQL database or some of the other file formats I'll get into in a second, we would typically save, say, pressure as a double. A number of, let's say 1000.24 might be a pressure reading we would see. If we want to save that into an image file, we're going to have to convert that to an integer between 0 and 255. That means we're going to lose precision. And I don't think we're going to lose so much, though. I mean, ultimately it comes down to the range that we see in that variable space. So we would need to know across the entire sampling of, the entire time span. Like, we would need to know what the lowest pressure and the highest pressure were during the entire historic span that we're looking at. And then the lowest would be 0 and the highest would be 255. And then anything else would be, scaled appropriately and then converted to an integer. So we would lose decimal points in that conversion and therefore precision. So an image file is lower precision, but the advantage is that it saves more efficiently. It requires a lot less space to save, which translates to higher read speeds with these images when we want to use them later. But with that said, we have to convert them from a JPEG format into a NumPy array, and that goes through the Open Computer Vision library, and I don't know how much computational power is required to do that. I've never done any sort of speed comparisons with opening a JPEG and converting to a NumPy array versus reading, I'll go to the next file format, a pickle. Now, a pickle format is something that you can use in Python quite easily. You can save just about any data structure as a pickle. So if we have a n-dimensional NumPy array, we can save that just to our hard drive as a pickle file. Same thing with a pandas data frame, and we don't lose anything. We don't lose precision on any of our stored variables, and the file format's pretty efficient. These files are not going to be as small as the JPEGs because we're saving, again, doubles, and there's only so much compression you can do with that. But a pickle file has the advantage of containing, we're not limited to the number of color channels here. We can have as many layers and as many variables saved in there as we want. So for a given timestamp, we can save everything that we want to look at. You know, U component of wind speed, V component of wind speed, pressure, temperature, relative humidity, you know, cloud cover percentage, anything that we want to save, we can throw that into a pickle and also do that for every layer, every pressure layer that we want to look at as well. And so I think the pickle is probably the easiest to work with, and there's a little bit of time and overhead associated with reading that. But again, I don't know how that compares to the JPEG route. This is something, again, I'm not going to be worried about myself because I'm using this MySQL database, and I'll be running multiple threads to sort of make up for the fact that, you know, running a query is kind of slow. But I do that across multiple threads on multiple computers and then throw them into a queue, so that makes up for that. But you know, in terms of, you can do something similar with JPEGs and CSV files, but it may be less necessary to do multi-threading with a pickle, because I think reading those pickles is pretty quick. So anyway, let me just move on from here. Again, I am going to be sticking with the MySQL database, and I'm going to experiment around with this web API for ERA5, and if I can make that work relatively well, then I'm going to go that route in the long run. But for you following at home, if you don't want to go and build yourself a MySQL database, feel free to, you know, just experiment around with pickles and image files. It's also a viable option. Those are just a couple parting thoughts on that format. Within the algorithms, we've got all of these different options. There are so many, you know, that aren't even on here, in fact. Support vector machines. I'm not going to talk about these too long because I don't think they're really applicable here, but these are great for, you know, training, you know, smaller data sets where you can fit all of the historic data, the training data, into RAM, because that loads very quickly, and you can, like, these are designed to essentially iterate over that. But when you get into batch training for bigger training sets, they don't really work that well. There are ways of doing it, like training incrementally, batch by batch, but I have had very limited success with doing that in practice. I wouldn't recommend it myself. I think neural networks are better in that application. But if you have a small data set, support vector machines are fantastic. And you know, I would recommend for anybody that hasn't checked it out yet, Andrew Ng has an awesome Coursera class where he gets into a lot of the mathematics behind various traditional machine learning algorithms, and he spends a lot of time on support vector machines. And you know, these are really cool in the right application, so definitely check that out. And same thing with random forest. These are a more traditional sort of machine learning algorithm, but they're fantastic in the right situation. The reason for that is because they can do feature importance analysis as well. They also work just generally out of the box on a lot of different problems. They'll give you very high accuracy models with very limited training sets. And so these are fantastic, especially for classification problems, but you know, also for regression. And there are ways of doing batch learning with it, but from everything I've read, I haven't tried doing that myself. They just, they require a lot more data to get the same performance. And so I don't think they're necessarily applicable here. Also, you know, we're working with spatial data, and both support vector machines and random forests like to deal with numerical data. And so I just, you know, when you're dealing with an image, it's not necessarily, or, you know, say a grid of data, I just don't think that these are really going to be the best choice. But there may still be a role for them, and I'll get into that later. Convolutional neural networks. Now these are used mostly with image data. So this is a form of neural network that is extremely popular. Batch training is how they generally work. Yeah, with all neural networks, they do the training in sort of like little small steps. As you get a sample, it goes through and trains and updates the weights you know, between all the the neurons, and it's just a very flexible you know, setup that can handle huge amounts of data very well. The only problem, and it's not really that big a problem, but they're generally used for classification, not regression. That doesn't mean they can't be used for regression. It doesn't mean they're not used for regression. It's just the most common use is with classification. So there aren't a whole lot of examples of using convolutional neural network for regression, but I found a few. I've experimented around here. You see if I can spit out latitudes and longitudes, and I can, and it works pretty well. So the best practices though are a little unclear. I'm doing this trick here where I'm feeding the center of the storm, the latitude and longitude, as a pixel on a white image in one of the channels, essentially. And that is, it seems to be working when I do the whole world view, but there may be better ways of doing it. I don't know. We'll get into all that more later. And recurrent neural networks, another type of neural network, these are really great for working with sequential data, time series modeling. They're not usually used for image data. I think there may be certain applications where people have used one of these, say like predicting the next frame of a video or something along those lines. But generally these are used when you're looking at a, say, plot of something, like for instance, solar radiation throughout the course of a day, and you want to be able to plot a future point. These things are great at learning that sort of stuff, especially where there are cycles involved. So recurrent neural networks, I think there may be a role for these, especially when we're dealing with the track data, which is numerical data and it's sequential data. That would lend itself well to a recurrent neural network. Okay, generative adversarial networks are fairly new, and they're really cool. They came out back in 2014 with a paper published by Ian Goodfellow, who has since been named the GAN father. He gets a lot of press, and I'm really glad to see that. It's very rare to see a scientist or engineer gain such world renown as Ian Goodfellow did. And these generative adversarial networks are a game changer for a number of reasons. Now, the way that Ian Goodfellow explains how these work is by using the metaphor of a counterfeiter and a cop. The generative network takes on the role of basically the counterfeiter, trying to create fake money that would pass for real money out in the real world. And the discriminative model takes on the role of the cop, trying to figure out, is this real or is this fake, and catch the counterfeiters in the act, so to speak. So over time, the counterfeiters get better and the cops get better at picking out the fakes. And they play against each other, essentially playing this game, making each other better over time, until in the end, the network as a whole is spitting out counterfeits that are virtually indistinguishable from the real thing. Now, there are so many applications for this. A lot of the different applications that we've seen lately are, I think, fascinating. In China, they created a fake AI newscaster, an avatar of a newscaster, and they marry that up with a text-to-speech engine, and this newscaster is able to get up and read the news. And it's an AI completely generated from a GAN. And there are so many other applications too, like really cool systems where you can feed it and like train it based on like an artist's rendering of a scene, a photograph or whatever. And with those pairings, you can eventually train this to, give it, say, a photograph and then spit out a Picasso of that photograph, or, whatever, like some sort of artist rendering of that picture. And then you can do other things like train it so that it can look at a map and generate a satellite image of that area. It's really interesting, and there are a lot of applications, and I'm wondering, and one of the things I've been messing around with here is, can we feed it, say, a snapshot of the world, either satellite images or maybe some gridded data, and then have this then spit out a forecast, like what will the world look like 2 days from now? And I've actually been doing a little experimentation with this, and I've had some limited success. So I'm going to go over some of that in a little bit, and I think there are definitely some new tweaks to that process that I want to mess with over the next week or two. But this is very, very promising. So I definitely want to try this out. It's definitely unproven. There are not many examples, but there is one implementation I found, Pix to Pix, which allowed me to rig something up pretty easily. And I think if we can make this work, we'll be the first, which is always fun. Now, reinforcement learning is not really going to work here. I'm just going to be upfront about that, but it is a really cool area of deep, deep learning. And well, I mean, the easiest way to explain it is if we can gamify this system somehow. If we were able to say, make a game out of predicting the weather correctly, we could make this into a reinforcement learning problem, but we would have to code it up into what's called an OpenAI environment, because most of these sort of out-of-the-box implementations of different algorithms, of which there are numerous reinforcement learning algorithms to choose from, require that you have an OpenAI environment. And coding up that OpenAI environment is tricky, and you basically have to be able to gamify the problem correctly, and that there's a lot of ways, infinite number of ways of doing that. You have to dictate like what will the environment say is the observation space, like what can you see as the game player, and then depending on the action that you take based on that observation that you're making, you get a reward. And what will that reward be? Are you going to reward, more accurate predictions way more than less accurate ones? I mean, is there some sort of function there? There's so much flexibility, and coming up with a solid environment representing the game that you're trying to play is a lot of work. And then within that, then once you get into tuning the AI, the neural networks that run the algorithm that's training on that, I mean, that's a whole nother level of iteration that you have to go through. And so reinforcement learning has a lot of potential, but it's also probably the hardest to implement. And I just don't think this is the best application for it. So I'm not going to do that here. Now, a hybrid model. Now this is, they call it the fused model. I mean, whatever you want to call it. In these papers that we've been reading, they've done this fused model approach where they have one branch that trains based on the wind speed, the U and the V components of the wind at different pressure levels. Another one that does that trains on pressure, and then a third branch that trains on historic tracks. And they all get brought together by a fourth neural network that sort of looks at each of those three and then puts them together and says, all right, well, in this specific case, I don't know. It's always a black box, but it may decide, all right, well, these two agree, this one doesn't, so I'm going to go with what these two are saying, or whatever. That last neural network will bring those results together and then spit out a single output. So this is a really cool way of doing it. And actually with Keras, which is the high-level API for TensorFlow, it used to be separate, but as of TensorFlow 2.0, Keras will be the high-level official API for basically creating neural networks. And I've been using Keras for years. I love it. It just makes it so easy to create very complex models, multi-input, multi-output models specifically, which are essentially what these fused models are. You have different branches of the neural network that all get pulled together to spit out, say, one output, or maybe multiple different outputs at different sections of the system. And Keras just makes that so easy to do. So that's one route that we can take. But that said, coming back to the random forests, you don't necessarily need to build a fused model out of pure neural networks. We may be able to, if we wanted to, combine different machine learning algorithms together, train them separately, or go way above and beyond and build a kind of convoluted way of training them all at the same time in real time together. But there are ways of kind of combining multiple machine learning algorithms together to get at the same sort of effect as a multi-input, multi-output neural network. So we might want, instead of having our fourth, the bottom network that spits out the final output, instead of having that be a neural network, maybe it could be a random forest. There are ways, things that we can consider doing there, but honestly, Keras makes making multi-input, multi-output neural networks so easy that why would you do anything else? That's my thinking. So I do think we're eventually going to get to this, or we may get to this, but first we need to assess some of the feasibility of taking the other routes. So looking at GANs and looking at convolutional neural networks and looking at recurrent neural networks. I think the first step here is look at those three and how they may work with the data that we have, and then we can think about putting those together in some way. And a generative adversarial network, it doesn't necessarily need to be pure convolutional neural networks within both the adversarial and the generative networks there. We could have a more complex structure for each if we wanted. I think theoretically that would work. But I don't think we need to do that, get into that just yet. First, we just need to test the simple sort of approach of using out-of-the-box pix-to-pix GAN to forecast future states of the world, and then look at, like, say, gridded data and see how you might be able to use that with a basic convolutional neural network, and then see what we may be able to do with historic track data with a recurrent neural network. When we do those three things, I think we'll have a better sense for what we may want to do in terms of a fused model. So that will lead us to the next part of this. All right, so anyway, just to quickly recap, I just want to go back. Data sets, we're going to use HERDAT. I definitely want to look at ERA5, but I need to assess how quickly that I can access that. There's simply too much data for me to download. I may be able to cherry pick what I want to use and then save that to a local MySQL database. But I need to really dive into that some more. So I'm going to do that this week. NOAA Reanalysis, I've downloaded. I haven't really dug into it too much. I have to bring that also into my SQL database. And gdas, I have been experimenting with that a little bit more, along with Wavewatch. And those are great sources for data. But with that said, I think that whereas my preliminary sort of work is going to be focused on gdas and NOAA Reanalysis and maybe Wavewatch to some extent, I do want to look into transitioning to ERA5 because it is the gold standard and the sort of the best data source that I probably have access to, at least from all the reading that I've been doing. So whereas experimenting around with these formats may be fine for now, I definitely want to see how I may be able to use this moving forward. And then data formats, I'm obviously using MySQL database, but I need to do some experimenting around with the web API. I doubt I'm going to save anything in terms of image files, but maybe, probably not, but maybe. Definitely not pickles or CSVs, and definitely not the original image files. So I'm going to be focusing my efforts here, and then within this, basically these three are what I'm going to be looking at initially, and then I may potentially start stitching these together in some new ways to build a hybrid model, depending on what I find when I work with these. So that's going to lead into the next week. But before I get into that, I can go over some of the preliminary work that I've done, both with the Generative Adversarial Network and with the Convolutional Neural Network. Haven't yet gotten into this one, but I don't want to save everything for next episode, or that episode is going to be 2 hours long. So with that said, let's jump over to that. So this is the CycleGAN and pix-to-pix implementation that I built this on. This is written by Junyang Zhu and Taesung Park, supported by Tongzhao Wang. Now, if you look at the examples here, this is important. This is how we have to set up our training data. We have an A and a B image, and it doesn't matter which order they're in. That's a setting that we can choose later, and this algorithm is able to learn how to convert either way. It just depends on how we set up our training set. So in our case, what we want to do is create pairs of satellite data. Now, I'm going to take one step back before I get into the code that I use there, because you first have to understand how I have all my data saved, where I got it from, all that stuff. So let me see, satellite image downloader. This is the code that I used to extract the satellite images from NOAA's site here. So if I just actually go to this website, you'll see where this all comes from. I covered this earlier in the episode briefly, but yeah, you can just see where it comes from, like now that we have the code up. So if I were to go to, this February 22nd, 1994, there's always this gridded image category, and I don't know if this predates what we'll be able to get, but the water vapor images, yeah, you can see it doesn't have full satellite coverage of the world yet in 1994, but later on we do. So this is a very, very cool image. If we go and click on it, you can see the URL up here is simply, this beginning part, and then, the four-digit year representation, month, day, and hour. So that's easy to replicate and iterate through in Python. So that's all this script does. All it does is it essentially goes and creates a set of strings and iterates through them, and then creates a URL with that string set, saves that image to this directory here, and then moves on to the next one. It's pretty easy to do. And once we have all those images, we're then able to use some other code. Actually, also, let me go back to here. Once we have those images, then the next step is that we need to basically stitch them together into a single image. So this code wants, say, this zebra and the horse image to be just really one image together. And yeah, actually, so CycleGAN's a little different. I really should be showing the examples from Pix2Pix here, because we're using Pix2Pix. So we're going to want one image with both the day and the night scene, basically stitched together. So how do we do that? Well, first I'll show you what I'm talking about, so it's a little bit clearer. I think I saved all of these, yeah, right here. So here's an example. We've got the satellite view of the world here on the left on August 2nd, 2014, and on the right, if I can zoom in, this is August 4th, 2014, so 48 hours later. When I first went through this, I only did it as 6-hour difference between now and the forecast. So just be aware of that when I show you the results in a little bit. It's pretty easy to rerun it. It takes several hours, and I don't have the time at the moment. This was really just a proof of concept to see if it would work. And anyway, so once we have these image pairs set up, which we do by running this combine pairs script, which I wrote as a modification of their own, combine a and b.py, then, we can begin training. And I generally do all my code, and I keep pulling this up here to show you the code, but this is called Spider. It's an IDE available through Anaconda. So I'm in Windows right here. You can get Anaconda in either Windows or in Linux. I think you can also get it in Apple's OS too. But basically we use Spider to not only show our code, but to debug it and also visualize variables. It's a really great environment to operate in. However, it has limitations. It's annoying to pass command line arguments through here, this IPython console. Generally, we would want to go out into the Anaconda prompt and run this train.py function there, because it does need, right here what I have highlighted. These are all the command line arguments that we need to pass after just straight calling, train.py. It's actually all that. We also have to send it the path to the satellite imagery data, which this is actually not even correct. But this is something that you would need. Like I would have to copy and drag this all over, or I can put in, you know, F satellite imagery here, which is where it's all saved now. Or actually, I think it's M drive satellite imagery, whatever, you know. But regardless of where you have your output data saved, you're going to need to set all these. And, you know, we're using Pix2Pix. This is the file, no, sorry, this is the folder name where all the output images get sent. And this is the direction, because you can set this to train in either direction, A to B or B to A. Crop size 1024. It doesn't sound like they recommend going above that. This thing really did push my GPU to its limit when I was running this. And again, I have an older 980 Ti. If you're on a 2080 Ti or something like that, or a Titan, an RTX Titan card or something like along those lines, then I'm sure you could get away with upping this significantly. Now, the last thing that we want to do is also set the no flip setting. And I'll show you what that does. So when I trained this the first time, it did something a little strange. Let me see. So this all gets saved to your output folder. The file name is within checkpoints. So right here I did, or was it name output? You know, when I ran this last time, it was experiment_name. So I go in here, it's got all the checkpoints saved, and it's also got the results. So I gave it those input sets, you know, A and B, which were the current state of the world now, and then the state of the world, in this case, 6 hours from now. And then it went through and learned how to take satellite image views of the world now, and then construct satellite views of the world 6 hours from now, which is really cool. However, you can see if you look at some of these, the waves, the weather is kind of moving in one way, and on others it's moving the other way. So if I open, say, this image, everything looks a little, you know, low resolution compared to the other, but you know, this is clearly the US, and you can kind of see South America here, and you know, the shapes of the continents are all what you would expect. However, if I go up here, it's all flipped. So that's what that no flip setting is doing. It's doing something that's referred to as data augmentation. So in a lot of cases, you know, we don't have a whole lot of data to train with. Data augmentation allows us to essentially create data from existing data in hand by, you know, doing small little adjustments to it. You can have, you know, crops from different parts of the image and send it those instead. It makes the learner just a little bit more generalized in that way. So sending it flipped images, you know, this is essentially, it gives it another sample to draw from. However, in our case, I don't think that we want that, because, you know, as we know from the Coriolis effect, you know, we're going to see fluid flows going in one direction in the northern hemisphere and the other direction in the southern hemisphere. So if this is flipped, you know, that's all not, it's not going to learn that, you know, or it's not going to learn it correctly. And I think that may be why we see some of the strange results we do. And I'll show you those right now. So we have the real input, and this is the current view of the world now. Let me go to actually an example where it's the right way. So epoch 11, real. So this is the view of the world. Is that one flipped? That one's flipped too. All right, let me find one that's not flipped. Here, 9. Okay, so 9 real A. That one looks right. Okay, so here's the input, and then the outputs. 9 real B, and I'm gonna put this over here. 9 fake B. Okay, so if I zoom in, now that's not bad, but you know, you can see they're not identical. There's some features on here that are definitely a little sharper on the real one versus the fake. I don't know how much of this is due to it learning incorrect swirling patterns, you know, because of the flipping during training, or maybe it just didn't train long enough. But this is what it's kind of viewing. It's imagining that the world is going to look like this, when in reality it looked like that. It didn't train that long, and but we can still see that it's far from perfect. I mean, I would be surprised if it was able to become perfect from just going through like these couple thousand images that I have. But it's still pretty impressive, I think, that it's able to even do this. You know, basically draw what it thinks the water vapor concentrations in the atmosphere are going to look like based on such a small amount of training data. So this gives me a lot of hope that we can come up with a design that may work here using maybe multi-channel images that are generated from grid data instead. You know, this was just a really quick experiment. So anyway, so that was the first piece of this. Now the second experiment I did had to do with just basically testing some of that gridded data with a convolutional neural network. Now, I'll show you. So this is the satellite image downloader, but for the rest of the data, I was able to grab most of that from FTP sites, and I'll put those FTP links in the video description. And once you've got an FTP site, I personally use FileZilla, but you can use whatever one you want. And one thing to be aware of with FileZilla is, you know, 10, 20 years ago when I would use FileZilla to download things, it was a simple installer. But nowadays, you know, I mean, they got to make some money somehow. So the way they do it is by loading in, you know, software to the installer, and you have to decline to install it. It's one of those situations. So just be aware of that. Make sure you know, click carefully through when you install this, so you don't end up with something that you don't want. And you know, it's a pretty decent tool otherwise. So you know, you're able to connect to, in this case, this is the archive site. And within here, you know, you can see they've got so much stuff. So gdas1 is the primary gdas data. And then they've got reanalysis folder somewhere. Here's reanalysis. So we've got the reanalysis file directories. And then I believe there's a reanalysis 2 somewhere too. But regardless, forget where that was, but I definitely downloaded both. Yeah, so we've got a lot of really good data that we can work with here. And then there's another FTP site where I believe I got the Wavewatch data. So the Wavewatch data, though, that comes in grib format. So I'm going to switch over. This is my primary machine, but I use TeamViewer to remote into my other machine, my Linux computer, and I have that here. Now, let me go to combine grib data stacked. I'll try to go through and add comments so this is a little bit clearer. So what this script is doing is it essentially is just looking for, you know, a bunch of grib files in a particular directory or whatever, using pygrib to open those. Now the reason why this is running in Linux is because pygrib is not easy to install in Windows. You need to install from source, which if anybody out there knows what I'm talking about, you know, I mean, it's doable. It's just annoying. Whereas in Linux, it's simple. You just pip install pygrib and it works. So anyway, as I switch over, I always have this up and running anyway in the background. And this will go and read each of those files, extract the U component of the wind and the V component of the wind, and then go and use Pandas to essentially stack all that together into a single data frame where I have one column for U, one column for V, and then, you know, there's a multi-index sort of setup with you know, we've got what is it, latitude, longitude, and the timestamp. And then that all just gets saved to MySQL database. Now here you can see, here are my different grib tables. This is grib data stacked. I don't use the other ones anymore. Those were just kind of, I should probably drop them. But this is actually not even my most current database overall. I have a whole nother database that I switched to, which has all my GDAS data in it and reanalysis data and whatnot. So they're just too big to all have on one hard drive. So if I go into here, you can see date, time, latitude, longitude, U and V. One really important thing though, oh, and let me just point out, this is MySQL Workbench. When you install a MySQL database, this is a tool that you have easy access to. And MySQL Workbench, it's so much easier to, do all the sort of maintenance stuff, assigning different options for your database, like timeout settings and things like that with MySQL Workbench than anything else. Also, when you're in here, you can go to this nifty alter table setting and make sure that your primary keys are all set correctly. Now, you always want to make sure you have primary keys set correctly in a MySQL database, because that significantly speeds up your query times. When I go and start searching for things based on date, time, latitude, or longitude, I'll get responses back much quicker. And that's the unique set of 3 things that I need to identify a point. I shouldn't have multiple latitude, longitude, and date time points. There should just only be one. And at that, I have my U and my V component of wind speed. So that's what that code does. It goes and just iterates through each file. Oh, sorry, wrong one. Iterates through each file and sends those to the database. Now, it uses multi-processing. So, this months list fast, I found this online. I think it was on Stack Overflow. And I do link to the original source of it here if you're interested. But I just use this because it's a really quick way of generating a list of dates between a start date and an end date. And then that becomes my master list that then gets mapped in each of the processes. I use 6 processes. We'll go and take a 6th of that list and apply, run this read grib function on that. So it's really quick, and I think it went through. It might have taken a few hours, but yeah, it's worked out. I was able to create my database, which in turn allowed me to do a sort of a cluster approach to this convolutional neural network problem. So once I have all that grib data saved in MySQL, from here I was able to go and use this sample generator code. And I'll put all this up on GitHub. I think I might have a slightly updated version of this. So I'll make sure that I have the latest. But this, I'm not going to go through every line of it, but I'll tell you kind of the gist of what it does. Uses this library called Pika, which is a Python wrapper for a RabbitMQ queue system. Now, RabbitMQ it's a messaging system where I can go and send samples to a queue on a local area network, or I think you can even set it up over the internet. But yeah, so between my 2 computers here, I'm able to set up queues. So what I do is I have this will go and read samples, training samples, looking at a specific date, time. I'll get my latitude and longitude of the current storm, along with the U and the V component of the wind speeds from around the world, and I'll have all the training data I need for my convolutional neural network put together and then sent to a queue. And the advantage of doing this is that running a SQL query is slow. Even if it only takes a few milliseconds, which I believe these might take a second or 2 each. It's definitely slow enough that it will be the bottleneck in our training process. But if we use a queuing system, which doesn't need to do any searching, it just stacks the output data all together, and then when we want to use it, we just pull the last one off. There's no sending a query, waiting for a response there. We just grab the next one in the queue. That's really quick. So what we're able to do is set up multiple threads on multiple machines. I'll go and run sample generator in 4 different consoles on this computer, maybe 4 consoles on my Windows machine. And then I'll have one console that's my learner. And that will be on my Windows machine because that's where my better GPU is. And that's this code here. So then this will go and, learn, create the neural network, create the model here, and just keep downloading the next sample. So, it worked pretty well. But I need to go and update this so that it looks at more variables, sort of mimics the behavior of that fused network a little bit more, and all that. But one other thing I need to point out, that when this sample gets made, the training in this case, I was creating like an image, like a channel, like basically like a JPEG image with multiple channels. One channel was the speed, in the U direction, the east-west speed. V was the north-south wind speed component. And then the third channel was essentially just a bunch of zeros with a 255 located at the latitude, longitude coordinate point, where the center of the storm is, or the one that's closest to the center of the storm. So that became my input image into this convolutional neural network. And that was, I thought pretty interesting. So this get sample, this is how it's working. The YPs and the Ys, these are the corresponding points, with the current center of the storm and then the future center of the storm for the training purposes here. And this is what all these stack things are doing, or they're stitching together these NumPy arrays into a format that works with the 3-channel convolutional neural network. And you can see, 3 channels in the input. So it's, I think this is a pretty novel approach. I haven't heard of anyone else doing this, mostly because I don't know a lot of people using machine learning to work with weather data. And I'll point out though that in the paper, the fused network paper, I think they did split the U and the V onto different channels, but I don't think they had the center of the storm as like another channel on top of those. Instead, they had to use a whole separate neural network to bring that in. And I just wonder which one would work better. So this was a bit of an experiment on that front. I'm going to keep working on that problem as well in this coming week. But this is where I'm at as of now. And, things are coming along all right. I just need to keep chugging along. Let me see. Plot SQL results hurricane. Let me just run this real quick. Yeah. Okay, so here are the results of the training. We can zoom in a bunch. 0.1. Yeah, 0.1. I believe this is the mean squared error. So the square root of 0.1 is something like 0.3. So we're talking about, because it's both latitude and longitude, might be about a 0.6 total error in terms of like a degree, and 1 degree latitude versus 1 degree longitude. It's not too different. So, that ends up being something like, I want to say 60 kilometers, I think 110 kilometers per degree latitude or longitude. So yeah, I mean, our error isn't great. That's what the sort of error that we would want to see at, say, 24 hours out or even 48 hours out. So we got a long way to go, but it is definitely, it's definitely better than I would have thought, at least for a first run at this, using just basically a proof of concept model here. Now, what I found here was that both approaches do hold promise, but more importantly, I found that I can successfully generate multi-channel image style arrays from gridded data that contains numerous variables, as well as a channel that can be used to identify the center of the storm that we're tracking. This approach could theoretically be adapted to work with the Generative Adversarial Network as well. And by doing this, we may even be able to identify the center of the future storm from the output image of the GAN. I still want to code that up, and it's going to likely take another week or so to be able to adapt that code and run it and get the results. But I hope that I'll be able to go over that with everybody in the next episode. Now, another thing that I want to try here is to hook up our historic track data to a recurrent neural network. As a couple of these papers have shown, past track locations of the storm can have a predictive value for the future location, and the recurrent neural networks are generally the best for dealing with sequential data like this. Now, I'm not really sure why the track data is specifically so useful. From my admittedly limited knowledge of fluid dynamics, if we know enough about the current state of the atmosphere, this closed system essentially, we should be able to figure out where the storm should go next without needing that track data. But the question becomes, how much is enough? It could be that the algorithms that others have used have simply not had enough information for the network to deduce the current storm's overall momentum and direction adequately. But I really wonder if this focused network approach, with wind speed, pressure, and track data would perform any worse if you took the track data out, or if you replaced that track data with something like, say, temperature or cloud cover percentage, or how much solar radiation is hitting that particular grid point at that point in time, so the day-night cycle that's going on, or maybe a combination of all those would negate the need for that track data as a separate input. I don't know. I think this is all worth experimenting around a bit. Now, with that said, though, there's a ton of data, and it would literally take me years to iterate through all the possible combinations of variables, especially since training one of these networks takes at a minimum hours and more realistically days. So for me to go and experiment with using track data versus using temperature data versus using solar gain or solar radiation or whatever it may be, that would take a really long time. So what I'm going to have to do is just sort of prioritize based on my own working knowledge of the subject here, atmosphere and fluid dynamics and physics in general. I'm going to have to prioritize a set of experiments, try them out, and then just call an end to it at a certain point in time and assess where I'm at, move forward, build a system from there. If we get to the end of this and we've built a prototype and it's performing well enough to meet our goal of being state of the art, then we've done it. If not, we can come back and repeat the experiment a few more times using different combinations of variables. Anyway, this is all gonna have to carry over into the next episode at this point, but I should have quite a bit more to go over with you guys then. For now, I think what we've got is a really solid start. We know what we want to experiment with. We definitely have a lot of different things that we can try, so the next week is going to be very busy. It's probably going to take me at least a week and a half, 2 weeks to get the next episode out, because honestly, putting together the video is almost as much work as doing the coding. So it's probably going to be week after next before I have the next one of these out. But I do anticipate the pace picking up a little bit from there, because most of the code is going to be written. It's just putting it all together. So anyway, make sure you hit that subscribe button so you get notified as soon as the next episode's up. And I'll catch you next time. Moonshot out.